And now for something completely different. We're going to talk about security in the context of service provider. So if you're listening to the last section, Akshat was talking about one of the key components about how do you deploy things quickly, especially in the access environment. There's something else that's interesting about access, and I'll bring this up because this is the first time you actually have to start thinking about some considerations that are really different from what you would typically think about in a service provider network. Access, think of the number of devices that are going out in a 5G build-out. It's a large number of devices. This is fundamentally the extension of your network. The physical locations where these devices are being deployed are becoming more and more varied. It's kind of funny from a security point of view, how much security in networking is still based in layer one. Think of all the security that you actually have in your core network that really functionally relies on physical layer security. Things are in a locked cage, it's in a secure facility, it's got biometric authentication, and ultimately there's probably men with guns who are actually backing that up. Once you start thinking about 3G, or about 5G deployments rather, and deployments in untrusted locations, you really have to start thinking about some interesting things. What we're going to talk about today is how we can start addressing this using some pretty meaningful pieces of technology that are built inside of the stack. So we're really going to cover three different things today. One is we're going to talk about a trusted platform and what that means, what it means in terms of trust in general, but also the technology that backs it up. That's about the first half of the presentation. We're also going to talk about how do we start to leverage these trusted platform components for operational benefit. And one of the things that we were talking about earlier is things like ZTP. This is an example where you can start to think about how do you leverage things like identifying a device and authenticating device maybe before you hand out a configuration, which has a lot of private and secret data in it. And then finally, we're also going to talk about some of the other considerations in terms of if you start deploying these devices in unsecured locations, there's actually a lot of relatively private information inside these routers. If somebody were to exfiltrate a router, which is a fancy security term for basically saying steal it, how many things on that router would you not want them to get access to? Think about how many authentication strings are there, how many passwords, how many other types of secrets, routing protocol adjacency secrets, logins. There's a tremendous amount of private data inside these devices, and we really need to start thinking about how we can protect it. But no security discussion can happen without a discussion about a threat landscape. So one of the things we needed to look at was how is security different in a service provider network? And the best way to think about this is think about who you're up against and what they're trying to do. Every week, we hear about a new breach, and it's usually happening in something that resembles an enterprise or more classic network. And what happens almost every single time? Somebody breaks in, they had pretty good tradecraft in terms of getting in, figuring out a way to get through that infrastructure and ultimately get to the information that they wanted. But their end game was exfiltrating that data for whatever gain they were looking for. So if you're a service provider, you have that concern. Providers get hit all the time. People are looking at things like account information from individual subscribers and such. But there's actually another problem that carriers need to think about that a typical enterprise doesn't think about. When you think about it, service provider infrastructure is critical infrastructure. If you're the network that's actually the primary national carrier for a country, you are basically serving almost as an important a role as a power grid or a water supply. How much of the nation's economy today is actually starting to move electronically? These are the things you have to think about as a service provider. So who are your adversaries and what are they trying to do? Well, we know that on the enterprise side, generally it tends to be a hit and run attack. When the attack is done, it's hard to detect while they're in process, but usually when it's done, they've gotten what they want. The difference is for a service provider, one of the threats is that attackers are actually trying to turn their network into an asset. Think about that for a second. How would you start to secure your environment differently if you think that's actually what's going on? I'm not going to go through all this. There's a really fun mental exercise we can have, which basically says, what would you do if you owned a carrier network? Think about the amount of implicit trust that is placed in a network. It could be something as simple. Literally, the best possible case is somebody comes in and does a write erase on your routers. It's a denial of service attack. It's happened plenty of times before. It's a best case because, one, you know exactly what happened and where, and you know how to remediate it. But what happens if you have somebody that really wants to leverage this network as an asset? What are they going to try to do? Well, maybe it's things that you can't see, or or that you would really have to look for. So without going into all of this, you can think of a couple simple examples. Like if you had access to a national network, you might want to steer traffic for surveillance. Maybe you've tapped one of the optical fibers underneath the ocean, and you want to make sure that the traffic you care about goes over that fiber. At that point, you may want to influence forwarding. That's a reason why you can use that network as an asset. There's a tremendous amount of man in the middle that you can do once you own a network as well. Think of what happens if you can inject a VIP into a core instance of a routing table. If you inject 8888 or 8844 or 1111, you can have lots of fun. So these are some of the things that are actually worth thinking about, and there's many more, but just as a security professional, the problem you're trying to solve is a little trickier, because ultimately your threat is it's not just people trying to break in, it's people trying to break in and own this for a long time and be able to come back into this network when they want to do something with it. So what would you do? So we all know a lot of the traditional layered security model, but there's something else that we have to do. How do you know whether somebody's actually broken in and compromised one of these systems? You have to actually take it a little further than traditional security controls. And you need to start thinking about understanding integrity. How do I know if somebody has actually broken in and changed something inside the platform? And really, this is why we're talking about trust. So trust is something that's been there for a while. You probably have platforms in your pocket today that have some level of trusted platform support. But this is something that we, as technology folks, haven't really had to dig into a lot. And it's kind of a brand new territory. So let's actually talk about what this means. So if we start to build this concept of trust, we're really trying to establish trust in the network by establishing trust in the platforms and components that build that network. So how would you do that? Well, there's really two things you can fundamentally do. You can build a security control that has the ability to actually prevent bad. We'll talk about some of those things that are built into the infrastructure. But the next piece is you also have to understand, have you seen any indications of compromise? Has anything changed? And we're also going to talk about why it's important to also understand tamper evidence inside the system. So I'm going to go through a logical concept here, because if you haven't dug through this, this is kind of brand new territory. I know when I first started dealing with this, you kind of implicitly understand some of this stuff, but there's a lot of detail here. And there's some things you've heard about in the news in the last couple of years about new technologies that are coming out where this actually helps put it into practice. So let's introduce something called a chain of trust. So let's say the end goal here is you're running a service provider routers, and we'll call this an iOS XR device. So at some point, you want to know, how do I know I have integrity there? Well, everything that runs in that operating system and everything that controls the hardware forwarding state ultimately relies on the code in that operating system. But what enforces the rules inside the operating system? What stops you from putting additional code on there? What stops you from accessing things you shouldn't? Well, most of those security controls are built into the kernel underneath. So you kind of really have to trust the kernel. The kernel is the one that differentiates who's root and who's not, for instance. Well, what happens if you ask the uncomfortable question, how do I know I can trust the kernel? Well, you want to start going back in the chain. How do you load the kernel? There's a bootloader. In this case, if it's Linux, and iOS XR runs a standard Linux distribution, so it also has a grub bootloader. So ultimately, you need to understand that you can trust that, because if you control the bootloader, you can make it load a different kernel. And then you start walking through another fun exercise where you start going further and further back. What loads the bootloader? Well, the firmware. In most platforms today, this is UEFI. Well, if you start asking the question, how much further back do you go, you actually get to a really interesting point that says, who do you actually trust? So what does this mean in practice? Well, ultimately, if you care about trust, you want to understand something called a trust anchor. And this is sort of the first piece of technology that we're going to be talking about today. It's not something unique to Cisco. It's something that we've spent a lot of time and effort actually building this technology, but you see focus on this from other platforms as well. If you see some of the new Apple products that have security chips, one of the functions of those is to be a trust anchor. You see similar technology coming out from some of the operations folks at the web scale providers, where they're actually manufacturing hardware that establishes a root of trust. So what's the point of this? I mean, there's this theoretical, how far back do you walk through the trust chain? But let's talk about why you would put something in there by looking at how you would attack a system. If you wanted to own a system, What most people think about when you're playing with Metasploit and you're trying to break into a system, you're generally kind of attacking the runtime. You're trying to break in from the outside, or if you get access, you're really attacking stuff that's running inside the operating system itself. And ultimately, what are you always trying to do? You're trying to get root, right? Because once you're root, you can bypass some of those security controls. Now, the next problem that you have is once you get that, remember, your goal is you want to be there for a long time. If you want to be there for a long time, you actually want to hack further into the system, because if you reboot the system, you'll reload the kernel and you'll have to break in again. So you want to be persistent. Well, what happens if you actually want to construct an attack so that how you break into the system and compromise the system would survive even if you reloaded it from a brand new OS install image? That's something called a bootkit. That's a pretty scary thing. It's something that doesn't just happen to network devices. It happens to servers as well. And this is really the end goal that you want to be able to protect against. And this is why it matters to extend the chain of trust. There's a technology that does this. There's something called secure boot. Who here has heard of secure boot and run into it before? Anybody played with it?
Hate it.
It's a pain in the butt, right? It's a pain in the butt because your laptop, for instance, has a set of keys, and it will literally not boot an operating system that doesn't have that. This is something you're starting to see in some of the new vertically integrated desktop platforms. Vendor A is starting to do more stuff with that. And you also find this now, especially Microsoft has been pushing this for quite a while. The reason you care on the server side is if you run something that's a critical server, people will try to attack it to steal keys and things like that. There's a lot of attacks against, for instance, Active Directory, where people try to compromise the OS using these kind of techniques. So you've seen a lot of work around secure boot in the PC industry and the x86 side. Now, the way this works is we went through that trust chain. Well, you can start to build verification into that trust chain. And what this actually does is it builds verification into the firmware, into UEFI. So actually, the secure boot that you hear about is called UEFI secure boot. It literally starts in that UEFI process, and if you have a bootloader and an OS image that's signed by the right magic keys, it'll boot. And if it isn't signed, it won't boot. It's a pretty powerful thing. This is how you prevent this kind of compromise. But there's a really interesting question you need to ask, which is, where did that UEFI BIOS come from? How do you know you can trust it? That's the next thing you need to solve. If you really want to have protection against things like bootkits, and you want to establish and maintain trust in these platforms, you have to have technology that actually starts even before the BIOS loads. So this is something called a hardware-anchored secure boot. Now, we're getting into some gory details about how you establish and maintain trust, but there's a couple takeaways here. The first thing is, this is a piece of hardware. You want to actually, what you're doing is you're taking trust and you're collapsing it down into some security component. It's usually a chip on the system. And that's a chip you implicitly trust. This is, by the way, not a TPM. TPMs don't do this. TPMs are like a little hardware security module that stores keys. This is actually a separate hardware component that you need to use to establish this root of trust. But the thing is that in order for you to actually have this continuous chain of trust, you actually have to have something that you know you can trust that cannot be modified, and that's why hardware matters. As we go through this entire discussion, there is one relatively uncomfortable truth about trust. Software can never protect software. You can always get in underneath software if you control the hardware. Any discussion about trusted platform has to talk about hardware, because at any point, you can make any system run any code you want, even at things like administrative privileges, if you own the hardware and the trust chain underneath. This is one of the challenges. And just to bring this back to the table, like, we're spending a lot of time going into gory stuff about security, and this isn't really classic networking stuff, but you as a networking professional, the reason you care about this is when you take a router and you deploy this in a front hall or mid hall or access network, where it's sitting in somebody's basement, where you don't have good controls or a good cage that it's sitting in, you need to answer the question, how do I know nobody got to this device without me knowing it and compromised it? That's why a lot of this matters, especially for these network build-outs. I'm going to use an example here. So this is how the technology works, and you actually see that it's creating a validation chain. It does involve this hardware anchor. This is typically custom silicon. You have to get it into the point where you're actually monitoring and measuring things like the CPU microloader. I mean, at some point, the trust discussion always gets to the point of how do you know you can trust the sand that went into the silicon? So you can take this pretty far back. But at some point, you do want to have something that you can point to that is actually a trusted component. So let's see what this means in practice. So I really started understanding this when I started thinking about what does everybody have in their pocket? So what actually serves a really similar role to what even some of these access routers would be? What's a device where you have pretty sensitive data on it? It goes in untrusted locations all the time. Lots of people can touch it. It runs an embedded operating system. Sometimes you have to run third-party code. There's a whole list of things where all of this starts to sound pretty familiar, right? So you can have a discussion of whether you choose vendor A or vendor G. But in this case, let's actually talk about what but let's talk about what this means in terms of actual trust posture. So let's say you have a device from vendor A. When I pull out this phone, you can either confirm or deny which vendor this is, but I'm sure the video can. You trust ultimately the software. That's what you interact with. But remember that if you don't trust the hardware, you can never trust the software. So what's interesting about this ecosystem is that the same vendor manufactures the hardware and the software, which means that you can actually build a consistent trust chain. If you have an ecosystem where the device itself, we'll call this vendor B, but generally when you interact with it, you interact with an operating system. All the systems and services you see basically come from vendor B here. The challenge is, if the hardware comes from a lot of other companies, let's ask an interesting question. If you're worried about this device being compromised, what vendor do you talk to? Vendor G, I mean B, or those other vendors? This is one of the key things about understanding trust and understanding trusted platforms, is that you actually have to start creating this validation chain. So if I was listening to this, the first thing I would start thinking about is a lot of these security discussions tend to be pretty theoretical. This sounds a lot like a black hat presentation. In fact, there have been lots of black hat presentations about this. Something happened last year, though. If we talk about why hardware anchor for things like secure boot matters, last year, for the first time in the wild, we saw UEFI bootkits actually being used. They weren't targeted at network gear yet, but they were targeted at laptops. But underneath the covers, when you look at the actual compute subsystem, how different is that really? And ultimately, these were actually creating bootkits by compromising UEFI. And if you don't trust UEFI, if your secure boot only relies on the integrity of UEFI, that's a concern. So this is one of the important things to consider is, if you're deploying things in untrusted locations, what is the technology that actually measures and establishes known good? But that's only half the story. If a tree falls in the wood, I was about to say something else, but it's a family show. But if a tree falls in the woods, how do you know, right, if you didn't hear it? Likewise, secure boot is the same problem. The only way you know secure boot is okay is the fact that it booted. If you flip some bits, secure boot will fail and it will come back with some cryptic thing that says, sorry, signature validation failed. The only problem is once it's booted, first of all, you've got two problems. It may have booted a year ago. And second, how do I know? How do I have proof that the system was actually good? How do I know secure boot was even turned on? Kind of an implicit problem. Secure boot doesn't actually solve that, by the way. Well, if you're going to solve that, you actually have to ask another really uncomfortable question, which is, how do you know whether something is trusted? So Akshat went up and gave a great presentation about ZTP. He's my coworker. I trust him entirely. But if I came up and asked Akshat, can I trust you, Akshat? What would be your answer? Of course, right? Who wouldn't tell you they're trusted? Now, Akshat's not the right example because he's a really trustworthy guy. But there's actually a problem where you cannot actually trust a device to tell you whether it's trusted. You actually have to verify. It's the old trust but verify. So it's actually important when you start thinking about establishing and maintaining trust, there's an element of measurement and actual reporting that you have to do to establish this. There's a way to do this. This is an eye chart. If you can pull out any of these SHA-1 sums, you're better than I am. But ultimately, this is what you do. You can start to measure the system. and you can compare what you've measured, whether it's things running at runtime, whether it's things running in a kernel, whether it's things like firmware images or even hardware signatures. You can measure this. And if you can securely store and report this, you can go back to what's known a known good value. If you can look at systems inside your platform and say, this is exactly what I've seen, these are hashes, these are unique cryptographically, I can then come back and combine these two and say, what have I seen that's changed? And that's really what this is about. Now, there's an important thing to bring up here. This is about establishing known good. The first thing that would come up in my head when I look at something like this is, let's not recreate antivirus. Let's not build huge signature tables where you're looking for bad. The problem is it doesn't work. For example, polymorphic code. You have polymorphic code that's different every time, you're just going to get a whole lot of garbage. But what you can always tell is whether something is exactly the same thing that you built. So there's some really powerful stuff you can build with a system like this. So how would you use this? So again, you can't trust entirely the system to report on itself, so you have to get these values out. I'm not going to spend a lot of time here, but if this is something you guys are interested in, I'm happy to get into this. But this is basically a process called remote attestation. And what this, there's a whole methodology for doing this correctly. And a lot of this comes from work around the Trusted Computing Group, the TPM folks. And it's this idea that if you can securely record these values, you need a protocol where you can request these and prove that those values haven't changed. And the details here are you have to have things like replay protection. So you start by each time you query it, you inject a little nonce, a random value, so you can't replay it. And then the values that come back actually get signed with a key that only this device has. And ideally, this is actually located directly in hardware. And as you start to operationalize this, there's some details in how you'd actually kind of make this work operationally. But then when it comes back to a service that would actually start looking at these, you can then start to compare, what did this system report? Do I have proof that it's authentic? Was it only signed by a key that is present on this device at a low level? And do I know that the nonce has changed and is unique to this request? And you can actually build up a pretty strong protocol for querying this data and now making a decision based on what you've seen as to whether or not you can either trust it or even understand what's going on inside of these systems with cryptographic proof. Most of the work done around this is typically focused around boot values. If you look at remote attestation, 90% of what you see is how do you establish the fact that you booted securely? The challenge is if you have something that's up and running for a year or two, you may want to start looking at things that are going past boot. So the other thing that's important is start to being able to extend the capability of measuring things that run at runtime. This means starting to open up looking at processes running inside the platform. And you can either do something where you're taking a secure hash of these processes, keeping these in a secure log that you can then query and report on, or even start to build a system that could actually block execution or just warn if it sees code that's executing that isn't signed properly. So there's a lot of powerful things you can do with these controls once you extend this into runtime. Because this is really where the tough part comes. This is not just an embedded system. It's also a system where you run third-party code. It's a system that runs for a long time. It's important to be able to have that kind of reporting. Without getting too much into it, there's things you can do. This is an example of a demo that we showed earlier this year where we actually introduced simulated malware and we did reporting on this. And we could actually see, do we see things running on this system that are not authorized to run? And you can do things like come back and call it yellow or say, I don't recognize this thing. And there's some pretty powerful things you can do. Now, we talked about trust. There's a whole discussion we can have about how we can leverage these technologies to establish and verify trust. But that's the first half of the story. I think the thing I want to wrap up with is everything that we've talked about here is really theoretical. It's important and critical. If you think of a network as critical infrastructure, being able to establish known good really matters. But all of this is great, but it's still not enough. Ultimately, you actually have to start creating value with this as well. How do you create operational value? How do you change operations? Akshat brought up an interesting point, which is ZTP. ZTP is going to be absolutely critical to doing large-scale deployment. So if you do that, you need to start thinking about security implications. The top one that I can think of is there's so many secrets in that config, anybody that can plug in and ask for that config can potentially get a secret. It's not hard. So what could you do? Well, we talked about the fact that there's hardware backing this up. This is something Cisco calls a trust anchor module. It's something that works a little bit like a TPM, but goes further. It also does things like secure boot. Well, this actually has some really interesting capabilities inside. It does strong crypto. We can use it for lots of strong crypto stuff. But you see that little line that says unique device identity? This is something that you've never had in a network device before. Everybody's got a serial number for your network device. That's what most people use. It's a serial number. But remember that if you start asking questions about trust, if you can't trust a device, how do you know nobody programmed your router to lie to you about what its serial number was, or even what version of code it's running? If something's compromised, that's what you can do. But what happens if you can actually start to cryptographically prove this? This is something that's built into every component of one of your service provider routers. It's also not common to just service provider. This is something that's built into all shipping Cisco products right now, is the ability to actually cryptographically prove unique identity. That one piece of hardware has a cryptographic key that is unique, and you can use that to actually test, is the serial number actually what you told it? Is it the same part number that you told it? And because it's an asymmetric cryptographic key, you can do really interesting things. You can sign stuff with it, or you can use it for things like encryption. So looking at things like ZTP, why do you care about having this globally unique identity? Well, you can now actually challenge the device to say, sign this request with your own private key to prove that you are who you say you are before I hand you a config. These are some of the things that can become possible if you actually have some of these trust technologies. And the thing I'll close on is something else that's really, I think, one of the most important things that we can do, especially for these devices in secure locations, is they hold lots of secrets. This is just a short list of things that are secret inside a device. Think of every single authentication string or password that's in your config. And now think about what would happen if somebody got access to that. One of the key ones is, no pun intended, is MACsec. MACsec pre-shared keys. If you have these, you can actually go back and derive what the actual traffic was inside a tunnel. These things matter. And the security teams, especially in some highly security conscious companies that are using MACsec, they really care about how you're storing these keys. So what can we do? Well, by the way, it's not just that. Third-party applications have keys too. Think of all the third-party apps that are talking to upstream telemetry gathering systems or anything that maybe has an access token and a key with that. Those are things that would be really fun to steal.
So, can I ask a question real
Absolutely.
quick? I don't even, but to you specifically, that actually brings up a very good question, I think, to me at least. From an XR perspective, are you guys rolling your own key storage? So like Vault or something like that, are you rewrapping that, or are you going to get into that?
Let's actually have exactly that discussion.
Okay.
So there's a couple things. So,
Sorry.
oh, no, it's like you've read the slides. Are you sure you didn't peek?
I did. I wrote it.
So there's a few things that we can do. So the first thing is realize that the config itself actually has a bunch of secrets. And it's important to have a couple things, really good cryptographic strength for those secrets. And then also a way that we can protect that and actually root that protection in hardware. So if you look at, I did a comparison to some of these mobile handset operating systems before. One of the key things that they offer is actually a keychain facility inside to actually protect keys for both their own use and third-party applications. So we can certainly start with stuff that we know we're keeping. There's lots of secrets in a config, and MACsec pre-shared keys are just the first piece. So there is something called Type 6 encryption. I'm not going to spend much time on this because you guys can read up on this on your own. But the thing that's interesting about MACsec is that it is actually doing two things. It's using a very strong cipher to encode any of the secrets in the config, but it allows you to cut and paste a config from one place to another because there's a master key that's used to unlock these keys. And it preserves an operational model of cut and paste. So if you need to be able to cut and paste a config, this is a way that you get to actually have very strong data at rest encryption, very strong protection of these secrets. And by the way, that master key is actually stored inside a secure storage facility, which is rooted directly to that unique piece of TAM hardware.
And you have API. I see you have APIs.
So we have APIs. Now, you probably don't want to play with our APIs because they make sense inside of XR. So one of the other interesting questions, and there's things that we can get from this. Type 6 was a very good place to start. So what you're going to see is that being pushed out across XR platforms and also expanded for things like keychain support. So other secrets management is also protected by Type 6. But there's also interesting questions like, should we extend this as a third-party API for external applications? So these are some of the questions we're currently looking at. And one of the reasons we wanted to have this discussion is to understand, like, is this something that you guys see as useful as a core service of this network operating system? So I know that we're running a little behind time, so I want to try to be good to our timetable here. But at a high level, we think this is what's really important about building and establishing trust. There's a few things that we know really matter here. If you're deploying systems in insecure locations, we want to have the toolkits hardware anchored to a low level that are very resistant to a lot of these high-level attacks from pretty motivated and funded adversaries. We know that it's important to start to create services inside the operating system to do things like secure storage and leverage that and be able to tie that back to that same crypto hardware. There's also other things that we can do about delivering more data plane security services and things like that. And also, more importantly, if trust is something that we think matters for customers, how do we start to report on this and build capabilities to query and report on this? So these are all the things that we think are really critical about going past a lot of the stuff we've already been doing about security. In the security space, you can always add more products and always try to find bad. What's fundamentally different about trust is you're actually flipping the model. Instead of looking for something bad, you're establishing known good. And we think that's a really, really powerful way to address a lot of the security challenges from these systems. And then use that cryptographic root of trust to actually deliver services that help things like protecting secrets or do interesting things like start to authenticate devices as part of ZTP with actual hardware-based keys.
Shipping today?
Everything that we've talked about there is, with the exception of anything that said that was future, yeah, it's currently in there. So we have Type 6 encryption that's using the hardware anchor. Likewise, we have the TAM hardware inside of existing platforms. That hardware anchored secure boot is in almost all modern shipping platforms. There's some older platforms that don't have it, particularly, basically, CRS does not have secure boot that's hardware anchored. However, all the modern shipping platforms do have that.
Awesome.
Any questions based on what we talked about?
Just one quick comment, and then I'll end. I think to your question about opening it up to third party, just off the cuff, I mean, I would say if you're going to roll your own, I think you have to open that up to third party, because there will definitely be scenarios where I need to get those secrets for some sort of orchestration, right? Just to get it out of my head.
Certainly. No, that's great input. I appreciate that.
Otherwise, I would say go away from your own